So what I want to do next is use the first law to think about something called a Carnot cycle. The Carnot cycle describes the behavior of a theoretical Carnot engine, which is a hypothetical, theoretical, perfect steam engine. So that's what we're going to go through. So this is a Carnot cycle. The basic idea is that we have a piston that is being driven up and down due to the state of the gas that is in this chamber below the piston. Oh, I am gonna need more colors of chalk, so let me get those. So these casings represent a temperature reservoir, and they will, at different times in this cycle, be relatively warm or relatively cold. And then, so we have the reservoir or the casing, the piston that moves up and down, and then this trapped gas that as it heats up, it expands, as it cools down, it compresses. So the basic idea is at first, this temperature reservoir is warm. That warmth causes this gas to expand, and we're gonna break down that expansion into two separate processes: isothermal expansion and adiabatic expansion. Now, in real life, if we had an engine, if we had a mechanism driven by this, these two things would be happening at the same time, but it's very convenient for us mathematically to think of them as separate processes and sort of break this problem down into the smallest possible pieces. So isothermal expansion, adiabatic expansion, then in this isothermal compression, my reservoir is now relatively cool. And then that cooling causes the gas to compress. Again, we break that down into isothermal compression and then adiabatic compression. So I think that's all I need blue and red chalk for. So a couple terms. Adiabatic, that's a word we know, we've used that word. So this is going to be a change in a temperature or pressure and volume of a system without any addition or removal of heat. So that's excellent. And then isothermal means at constant temperature. So the thermal there, that part of this word referring to a temperature, and then iso is, that just means constant. So isothermal means temperature is constant. So let's actually write that down. So hopefully you guys can already see how we made this problem easier on ourselves. The form of the equation for the first law that we're going to use here is... So hopefully you can see how these assumptions of breaking our processes down to an isothermal process and then an adiabatic process is going to make our life easier. Because in the isothermal, either expansion or compression, this term, my change in temperature, will have to be 0 by definition. And then in adiabatic expansion and compression, we will see that my dq is 0. There's no additional heating going on. So the work done is just equal to the specific heat times the change in temperature. So it's actually going to be the easiest part of this, is that in the adiabatic expansion, dq is 0, so the work done is just specific heat of the system times the change in temperature, and we could relate the amount of work done to a physical distance of this piston that's been moved. If this really is a cylinder, then at constant pressure, that change in volume, right? That's just the change in the height of the cylinder. That's the distance moved. That's my work output for an engine. So that tells me a lot about what this engine is doing. Hey team, we're gonna break this video here. We've learned about the Carnot cycle and looked at the work being done during adiabatic expansion and compression. And then in the next video, we will deal with the isothermal portions of the Carnot cycle to wrap this guy up. Okay, I'll see you over there. Bye team.